Today is lesson 2 of Solid chapter, and we're going to talk about the open-closed principle. We'll talk about various points at it, both ensuring securing code that is already working and ensuring extensibility that we can provide from the outside. And we'll talk about various ways and levels of how to achieve that. What is open close principle? How does it get implemented? What's the relation of plugins and middleware to OCP? What does hardcoding have to, what impact does hardcoding have to OCP? How do we choose proper parameters or the amount of them? How do extension methods help us incorporate OCP? How does Silk modifier help us incorporate OCP? Um, Interfaces and how do we utilize them for OCP? Polymorphism, inheritance done right. How do we integrate with third-party code? Um, and in general, what do we do to make our code secured? What do we do to make our code extensible? Properly extensible. So now let's look at the definition of open-close principle. Software entities, being classes, modules, functions, etc., should be open for extension but closed for modification. That is the key to the open-close principle. Extensibility and immutability of what is already working. And I'm talking about immutability not of state, but of actual code. Code that is working shouldn't be tampered with. So why do we need OCP? If we implement OCP, we'll have the following benefits. There will be way less changes in existing code, less chances of breaking anything with new functionality, easier to find different functionality, and new changes will be in isolation, in isolated complexity. So by adding new changes, we will not be increasing our complexity that much. And an excellent picture that says that if we simply want to put a hat, we definitely do not need to perform a brain surgery to our head. So if we look back at definition, open for extension, closed for modification. How do we enforce immutability of the code? Again, not immutability of state, but higher level immutability of code itself. And again, we need to code that way that it's not just about word of mouth and conventions, but it's about strict rules that cannot be broken. And it's not even an option to break them. You simply don't allow to break the code you wrote. So here you see a cat. You cannot fax a cat no matter what you do. So as ridiculous as this looks like, there is code that tries so hard to work against the intention that it has been made, but it simply doesn't work. They're doing it wrong. So, and that's a good thing because it shouldn't work. All that we pass shouldn't work with the functions because that was not the intention that we were going for. So the problems that arise usually come from poor Class design. Poor class design is usually littered with virtual and abstract keywords. Avoid those keywords because they do you no good. Instead of adding extra things through um, inheritance, through overriding stuff, consider simply add a new class, a component, swap an existing component altogether, and add new behavior like that, rather than overriding, because every override is a potential risk that you will break things, and we don't want to break things. Um, if you allow state of a class to be mutable when it shouldn't be mutable, you create a risk of it breaking. And to minimize that risk, we can use properties instead of fields, and specifically read-only properties instead of setters and getters at all times. Read-only properties, get-only properties allow us to restrict writing of data to the field, and that just makes things better. Reduces the amount of things that can go wrong with data itself. So next time you have private functions or setters and getters when you don't need them, just consider if you really need them. And if you don't need them, hide it. The worst thing that programmers often do is just in case make things public. So when you make just in case something, you create problems that can happen just in case as well. So you don't want to have extra choices that other people can make when using your code. You want to maximize the decisions not made. Minimize the decisions that anyone has to go through when consuming your code. And again, we already established that inheritance is not very good, and if you inherit, you can override stuff, and overriding stuff can turn something that is already working into a horrible mess. And we want to defend against that. And in C Sharp, for example, you have a sealed modifier on a class which prevents it from being inherited. Seal a class so that it will not be supported for inheritance. And when should you use sealed modifier? And the answer is more often than you do right now. And in the first place, if a class is perfectly fine designed, add a sealed modifier. Because don't just in case stuff, because it's a higher risk that it will break rather than it will have a meaningful addition. And also, for a class that overrides another class with abstract and virtual modifiers, you should definitely seal it. Because if you override it once, you can override it twice. And that makes things complicated. A complexity that you don't want, and a risk that you don't want as well. Now that we know how to enable how to prevent changes in code that works, we should also try to figure out how to minimize changes altogether so that we don't need to change code in the first place. How do we do that through design? Let's look at this picture for a round house. What is an issue with this round house? Well, what if we want a new floor to be added? What if we want a new wall to be added so that we could have rooms? new rooms in it. It's not very extensible, isn't it? Compared to a typical uh, sharp, square shaped house. So, what can we do about it? Well, how do we extend round houses or do we extend square shaped houses in our code? That's the question. In the early days of Solid, inheritance was a huge fashion. Everyone was inheriting everything because that was such a simple way of reusing code. That was such a simple way of adding new behavior. Simply inherit stuff, and here you have it, a class that did what it did before and a little bit extra. But that is a fantasy rather than a reality, because in reality, it is a big coupling of parent and child, and things break more often than not. Proper inheritance is fine on second thought, but inheritance by itself should not be used as a means of just reusing code. It has a bigger meaning. Inheritance should be used in order to create raw logical relations. Um, Things logically need to be the things that they are. For example, a parrot is a bird, so it's fine for a parrot to inherit a bird because it is a bird. Male is a human, so is female, and therefore it's fine for them to inherit human class. So logical relations. Inheritance, of course, should also be purely incremental. All that the parent could do, all a child should do as well. And inheritance shouldn't be deep, not more than one level deep. Sometimes two is okay, sometimes more is okay, but with every level of depth in inheritance, you create extra complexity that you do not want. So if we cannot inherit properly in so many cases, what is a better alternative? How do we manage complexities? And the answer is composition. Instead of inheriting stuff multiple times, have multiple components. And on top of having components, inject them from outside. Compose a class from smaller pieces, and like this, you have a proper decoupled logic holder, a container of sorts. Sometimes you don't have to inject dependencies themselves, but the point is that if some logic is unrelated, it should come from outside rather than be implemented inside, even if it's a little thing. Because otherwise you're mixing levels of abstraction. Because composition is a high level and implementation is a low level, and you should not mix those two. Hard coding, again, imagine if you have two functions that differ just in some target argument that they interact with. And then you have a third function that you need that interacts with a different target, and you just hard coded that target, and you're bound to just keep creating functions for every new target. So that is the most simple example of how parameters help us ensure open-close principle. Another example would be, imagine you are working with a class that returns all users that exist in the system. And for example, right now, you are treating those users as an array of people. So if you're treating them now as an array of people, you get uh, something as an array of people, and well, you just iterate through them, and that's fine. But what if you suddenly need to change the way you interact with those users and you want a list for some reason? What if you then chose to, well, a list is something that is nice, but I want a linked list or a blocking list or something like that. Again, you make a change, but then you realize that the and then from another different place, well, you need to do a different thing and another different output type. So again, you make a change, and then it starts getting confusing because you need to have two different things in two different places. So the point I'm getting here is that for output and input, if you don't need a specific type, you shouldn't be using that specific type. So for example, if the type won't change, for example, if you are returning some collection of users without the intention of adding more users, then there's no point of making that a list. A IEnumerable is good enough. Solution to inheritance is also a decorator pattern. And a decorator pattern simply says that, well, I can add incrementally changes to some existing method. So if I did something, I can do something more with every decoration that I make. How does this look like? So instead of overrides, we simply have a kind of wrapper that takes uh, a target for behavior and it does something with that target. It invokes the target method and does something on top. So here you can see we have notebook writer, and notebook writer all it can do is to write a note in a notebook. So notebook writer dot write is what every notebook writer can do. And if I have a property, a field, a reference to some existing notebook writer, I can add extra behavior to it. I can say, hey, notebook writer dot write a note and do something more. That is how Decorator works. I call the original and on top I do something more. That is Decorator. And you can compose Decorator with extension methods and have something like a comboed decorator like this one, where you initially have a plain notebook that just has in-memory text content. And then you can say, well, when I write content, maybe I'll write an email, maybe I'll log to a file, maybe I'll log to database as well. So like this, you can have a multi-level notebook content writer through extension methods and decorator pattern. Middleware also helps to ensure it's not method chaining because, well, it's similar to method chaining if you want to be um, if you want to seek similarities, but rather than chaining methods, you're just calling what the original called. So the last uh, the last container that contains basically everything will eventually call all other methods. So the difference from chain of responsibility, if that's the pattern you were referring to, is that in chain of responsibility, I would have a reference to next instance for calling, which could look very similar, but um, in that case, I would literally just be calling next um, next next thing in the line. I think the difference here is that there's always going to be the decorated target, unlike in chain of responsibility. Chain of responsibility is a bit more like linked list, where you will end up having no next caller in the chain. And in here, I'm always going to have uh, a reference to a thing that I need to call. So if you compare it to method chaining, then it's more like you start from the end, from the topmost thing, and then it just keeps calling the dependencies. And it doesn't matter start or end, it can have varying positions. That is the difference, I guess. Quite semantical difference. So logically it is method chain. Middleware. So the relation of OCP, open close principle, and middleware is that um, that middleware enables us to add a change for the whole application flow by doing something to all the inputs and outputs that we have before or after we get them or return them. So that's the benefit of middleware. For example, if we have a web API which, let's say, throws an error, we can use a middleware to take that error, maybe inspect it a bit, and, well, format it into a user-friendly message. Maybe treat it slightly special, apply a special format, and so on. So middleware allows us very powerful things across the whole application consistently. That's the power of it. Plugins is one more thing, one more technique that was a lot more popular back in the days, but nowadays it's seen more through game mods. For example, GTA 5 allows you tinkering with game prefabs, and you can, because the game developers exposed some, backdoors, some ways of changing the assets that game loads. Similar for Unity 3D, you can create editor scripts and add your own tools to the engine itself. So essentially, you're extending the game, you're extending um, the the engine with whatever you want. And lastly, I wanted to talk about the code smells that are caused by violating open close principle. How do you know if what you're doing is wrong. If you're checking on a type, doing if else statements based on a type or based on a field, doesn't matter much, you're likely to violate OCP principle. However, casting by itself is not a bad thing, but casting to check a type and based on that do logic is a bad thing. So if you do casting, ideally it should be casting for a class. Ideally it should be logical. It should be generic. Generic, like logic, specific logic shouldn't depend on specific type. It should be generic, polymorphic, or similar. So this kind of casting is not fine. We do not want to check what types things are and based on that do some logic. For example, calculating taxes. That's quite bad. However, this is much better. So here we basically say that, we have a dictionary of cached objects, some heavy objects that we don't really want to expose. Sorry, heavy objects that, how do we store something of different types in a list or a dictionary? The answer is we cannot easily store objects of different types if they don't have a base type. Everything is C# is an object, so we can store everything as an object. So imagine that you have a bunch of heavy objects that you can get by type. There's always ever going to be one of that object, and we use it for, let's say, cloning purposes or or just getting the instance to get the job done. But it's heavy objects that we want to work with. So we don't want to abuse in creating those objects, and we want to cache them. And this caching, this implementation is fine. Casting here, you can see, is fine. And why do we need casting? We get the type of generic T to know what type of object we need to work with. And then we say cached objects contains type. So if cached objects contains the type that we're working with, we return from our cached objects dictionary an object by that type. However, as you can see, the value is object, but we're returning T. So we need to convert this object into T. And since what we're saving in here is always going to match the type, and the object is always going to be of that type, we can safely cast it as T. So this, in my opinion, is the only safe generic cast that there can be. Like, generic cast is fine. This kind of cast is a smell and should be refactored to polymorphism. And now about polymorphism. Often we have switch statements, if statements based on something. So this example illustrated a switch statement based on a type. And this example illustrates a switch statement based on a property. So some enum or similar, or a string. So this switch statement can be refactored to polymorphism. So instead of having some tax calculator that has a calculate method and takes taxes and money, taxes that do basically nothing, just have an amount value and a tax type. So based on those, we do calculation, which is bad. And a better solution is to just have iTaxes interface with amount and complex calculation method, which takes money and applies taxes to that money amount. each tax applies does its own calculation. So we have polymorphism, and in the first place, we no longer need this big method, and we can simply utilize polymorphism and call it like that. One more code smell called Divergent Change means that sometimes classes, when we need to change a class, we end up changing multiple things in that class instead of changing just one. And we start thinking, why are we changing multiple things? What's the problem? And the problem probably is because, well, things might be out of place. And when they're out of place, we should split them. Splitting them helps because we isolate the two unrelated things, cutting all connections between them, cutting all ties, and, well, the only centerpiece will now be the class. So if A is not related to B and C is the place which contains A and B, it reduces the risk and it reduces the probability that A will break B or A will require B change, and also reduce the risk that either of those will require multiple changes in A, probably just one in C, sorry. Another code smell is speculative generality. So sometimes it happens that we make things just in case. We make deep hierarchies of inheritance just in case. Or in general, we split a class from its child into a parent just in case that maybe that part might be necessary. This is actually a bit more rare scenario. But again, we end up having the same problem as inheritance altogether. We simply don't need it, and there are better alternatives, and we really don't need to have things just in case. So if we have things just in case, don't collapse the hierarchies into one or two level deep inheritance trees, ideally just one level deep. Or ideally no inheritance, and just refactor that to composition. There is little point in having stuff just in case. Well, there is point, but inheritance is a construct that causes too many problems if left unhandled. So if you choose to do something just in case, choose a better way. Inheritance is not the way. We apply Yagner principle, you ain't gonna need it. You ain't gonna need those deep inheritance trees. You ain't gonna need this flexibility. Keep it simple and small. And lastly, sometimes we need to do something more than a third-party component, a third-party library enables us to do. We need more functionality. And what is the solution that we can apply in C# for such a thing? And the answer is extension methods. Extension method syntax has already been taught, so I'll just remind you, it's writing this, it's having a static method in a static class with this type member keyword. And if you write a parameter with this keyword, it works as if you are working with an instance of that class. At least semantically, by calling that method, will feel as if you're calling it as if it was an instance method. So that is a kind of how you can add the behavior that you need to library classes using the extension methods. Option B is to just wrap the library class in an adapter. So adapter basically allows you to provide that class any interface you want, and with that expose any functionality you want. That is all I wanted to talk about today. So, do you have any questions? Or rather, would you like to? Okay, just say any and I'll try to answer. Okay, a workable example. Sure. I can code on the spot. Composition versus inheritance. I know exactly a really good example that proves the point why composition is superior. So imagine you have a tile class. Tile as in, something that you can step on a game, for example, a game tile. That matters not so much. So I'll have a folder for bad, and we'll start with bad example. So here is a tile class. And what does a tile class have? Let's say it has a position, so a vector. Yeah. Position, public. Also, probably, if anything is stepping on it, so, or rather is occupied, maybe like that. Occupied. So by default, it's not unoccupied. Just one P. Occupied. I don't know. Anyways, that's the tile class. And now let's say we need to make this title move. So in inheritance-based approach, we'd say moving tile. We'd say that we can move it and moving to, let's say, a certain location will ignore the fact that it's get only. Well, I'll say protected set for simplicity's sake. Oh. Position. So this inherits tile. And position is location. Interpolate in between. Interpolate means that you don't just immediately teleport the tile, you move from one location to another gradually. So that is what a moving tile does. constructor. So far so good, right? You have a tile, you want it to be moving, okay? Now you have one more tile. So the tile that we'll add is destructible tile. So we don't need any of that. Tile. Okay. Okay, we don't want any of that. Let's do the inheritance. Public void destroy. So it just destroys the tile. Boom, done. Nothing special. And let's make one more tile. Offensive tile. Some tile that, you know, acts like a surface that can damage. For example, lava or fire or similar. Let's change the name, or more like rocket tile. So a tile with rocket. Public void shoot. Vector free, let's say to a location. Shooting, doesn't matter how. So what problem do you see with the current design that we have here? Or do you see any problems? We have just a tile, plain tile, rocket tile, destructible tile, and moving tile. What do you think? Is this good design or bad design? It's actually right now there are no issues with this, but the issues start, and there are no issues with the base class itself as well. However, there are major issues with what? There are major issues if you want to make combos. What if I want to have not just a tile that moves, but let's say we have statue, moving statue. You know, like an obstacle that blocks the way of a player or something like that. So that's awfully similar to moving tile. Another problem, what if we want to have a tile that can move and shoot rockets? Or a tile that can move and be destroyed? We are not really supporting in a sensible way combinations, because if I wanted to have a combo like this, I would need to have rocket, I would need to have destructible rocket tile, and I would inherit class. I would inherit the circle rocket tile. I would inherit the rocket tile, and I would add destructible logic here, which again duplicates code first and creates a necessary class second. So first problem, hard to manage combos. And second problem, new classes need to start over with similar functionality, for similar functionality. So also we have position C-P. And let's say you also moving statue, right? So that's clearly two problems that you already spotted. Do you agree that those are the problems? New classes, duplicate code, because I cannot reuse the functionality for moving something that is just a tile. And another thing, I cannot make combos if I inherit everything, because it's coupled. I cannot take a piece of it away and stitch it to another part unless I keep inheriting. So these two are clear problems with it's not about prefixes that our code smells, but definitely it suggests bad design. It's not about prefixes per se, though I do agree that they would signal something. But I would say that the bigger problem is that in general, if you see something inherits something multiple times, that by itself should be a problem. It doesn't mean that it is a problem, but it means that, hey, why is it done like that? Should it really be done like that? And especially if you start going to something like this. If I start inheriting the second time, then again, I should look at it closely. So what is a better solution? How does composition beat inheritance in this case? So I'll start from 0. And let's take the tile code, fresh tile code, which was working just fine for me. And what is a moving tile really? I can still have a moving tile class, and I will. And you said prefix itself can be a problem. Well, it's not a problem by itself. So what is a moving tile? I'll ask a question slightly differently. What is a moving tile made of? And the answer to that question is a moving tile is just a tile and a motor that makes it move. So a tile is what gets moved, a motor is what moves. So you have a moving tile. And now if I want to, have a location, these are private, read only. And if I want a location, my location will be, okay, it will be the location tile, position of location. And what else the tile have? It's occupied. Is occupied, and if I want a motor, so what can a motor do? A motor can move an object, locatable object, locatable, interpolate, and we say locatable dot position is vector free position. Let's create an interface. Vector free position. So tile is something that can be located because it has position. So like this. So now if we want to move something, we simply say motor move tile to position. The benefit of this is that the component for motor and the tile itself can now be reused. So I can add rocket class, public void shoot, vector free location, shooting rocket, and we can say moving tile with rocket. Will be pretty much the same, and we'll also have rocket. Rocket. So you have rocket, and if you want to shoot, you just call rocket. Okay, so you say rocket shoot far at. I guess just say position. Right. So the benefit of this, you might think, hey, we just wrote a bunch of redundant code, but all the complexity is actually not in wiring everything together. This is trivial. This took me literally a minute to write. The complexity, which I might potentially spend hours writing, relies in these methods of the components. This is just the wiring part. So by itself, this class does absolutely nothing. Yeah. So if we go back to the bad example, Rocket Tile is just awfully coupled garbage. It's nothing. Like it what is Rocket Tile even? It hardly makes a logical relationship to a tile. But if we say a rocket tile is a tile with a rocket, well, duh. That's what even the words imply and say. So it's much more logical, and when you get the hang of it, intuitive to make composition based um, approach rather than inheritance based approach. And now we solved those both problems that we had in inheritance. So what problems did we have? Well, we now have logic for motor, logic for rocket that will change independently and won't affect neither moving tile nor moving tile with rocket. It's just a construct for wiring things together, but it's independent of those two things. Their changes will not impact the changes of the composition itself. And now I can add a sculpture too. Which can also, so sculpture has a location, and of course I can have a sculpture that moves. So that is a sculpture. Readonly. And a motor. Motor is already done, so nothing there. And voila. Free location. New position. Interpolate. And we say motor move new position. What do we move? We move sculpture this time to new position. Boom, done. So that's the benefit of composition versus inheritance. We'll talk about more about this principle and how is it practically used in the next lesson tomorrow when we cover Liskov's substitution principle, LSP, L of solid. I hope this answered your question. And do you have any more questions? All right, awesome. I knew exactly about this example because there's often the same confusion that people have about this specific thing. And be careful if you watch stuff on YouTube about OCP, open close principle, because people on YouTube often explain this as inheritance based approach. And to me, it is absolutely outrageous and ridiculous. And if I see a video like that, I immediately write a comment. that it's outdated approach. Even though it's a classical approach, it's outdated approach, and we should be more modern about the way we do it. Also, a short note: what you see here is not what you would actually use. You would use abstractions. Yeah, full-bore examples suck a lot. They illustrate semantics, but they don't illustrate the whole point, the logical reason behind them. And I was saying this normally would have eye sculpture, eye motor, and so on. Because normally we depend on abstractions unless this is just a model. But this has behavior probably. All right, thanks for a great question. Before I go, one more thing that I would like to ask. If you can, please write one thing that you think you understood very well, and one thing that maybe you're curious about, maybe you would like to understand better. So write 2 sentences, short, concise. What was the highlight of this lesson? What you think you understood, and what is curious? What maybe you're curious about something that I mentioned, but you want to know more. And I'll be right back in a few minutes. Okay, I'm back. All right. While you write, if you write, I'll link the slides. So Kevin wrote, I just found composition over inheritance example to be excellent and practical. I'm curious about when you said you would code sculpture and motor as abstractions. If sculpture and motor is more than just a bunch of getters and setters and have some behavior, like, a tile, let's say, can lock a person or something like that, or a sculpture which, let's say, can be destroyed, is a destructible thing, has, well, again, is not inheritance based approach. But basically, if any of them have more logic than just getters and setters, having an interface is the way to go, and you'll see why, but that's outside of the scope of this lesson. That will be mentioned in, let me think, next Wednesday. I'll talk about that. It's too broad to talk about now, so I will not answer that question yet. To be short, you want to depend on abstractions and not on specifics, because it's easier to simply not care about the details under the hood when you depend on something. That's the short answer for it. Yes, live coding part, I agree, was very important, very useful. I probably would have made a code example in the slides, but probably having a code example in slides is not as effective as live coding it. So I shouldn't have too many code examples in slides and just live code it on the spot. All right. I think that was all that I wanted to say. Um, Next lesson, again, tomorrow, we'll talk about Liskov's substitution principle. So thank you guys for your time and see you tomorrow.